So oxidation-reduction reactions are also called redox reactions. And in a redox reaction, one or more electrons is being transferred. So somebody's going to lose electrons, someone else is going to gain electrons. Now, in order to keep track of who's gaining or losing electrons, we use something called oxidation numbers, or oxidation states. And so what it's doing is we're keeping track of who has what electrons or how many electrons, okay? So if I have a covalent bond between two identical atoms, then electrons are shared evenly. So for example, if I have O2, both oxygen atoms are going to pull equally on their shared electrons, and there will be no net polarity. If I had F2, again, they'll both pull equally hard, no net polarity. So when we have a covalent bond between two identical atoms, we're not going to have an oxidation number. But when we've got two different atoms, one of those atoms is going to pull more tightly on those electrons and have more possession of those electrons. They'll be partially negative. One of those atoms won't be as good, it'll be less electronegative, and it'll be partially positive. Now, oxidation numbers in covalent compounds are imaginary. They're imaginary charges. So it's not a true charge. In an ionic compound, yes, somebody actually gained an electron, somebody lost an electron, and so the charge is either positive or negative. But in a covalent bond, it's partially positive or partially negative, so we're kind of keeping track of that partial charge, okay? Now these are rules that we want to memorize for our oxidation numbers. Okay. Now, an atom that is an element is always 0. So if I had, for example, sodium metal, that would be 0. Okay. Oxygen as an element is 0. O3, still elemental oxygen, 0. Okay. So anytime we have a pure element, it's 0. When we've got an ionic compound, for example, NaCl, each of the ions in my compound have their charge. So in the compound NaCl, Na has a +1 charge, Cl has a -1 charge. If we have an ionic compound with polyatomic ions, so for example, Na3PO4, Na is still a +1 because it's a single ion, but PO4 is going to be different. PO4 as a polyatomic ion has a -3 charge. I would still have to discover the oxidation number on the P and the O separately. Okay? So for covalent compounds or polyatomic ions, I need to use the rules down here. Fluorine is always -1. It doesn't matter whether it's in an ionic compound or a covalent compound. Fluorine is the biggest electron bully there is, and so he always has a -1 charge, period. So in this case, HF, hydrogen's going to be a +1, fluorine's going to be a -1. PF3, fluorine's still a -1. Because I have 3 of them, phosphorus would have to be a +3. My charges in the entire compound, just like an ionic compound, have to cancel out. Okay? Oxygen is usually a -2. When it's an element, it's 0. When it's in a compound, it's going to be a -2. There's one exception, which is peroxide. Peroxide is a polyatomic ion. It's O2, 2 negative. So each one of those oxygens has a -1 charge. Okay? In this case, H2O, O is a -2. So each one of my H's has to be a +1 to cancel out. plus 1 plus 2, negative 2, they cancel out. CO2, O is still a negative 2. Because I have 2 negatives, I have to have 4 positives to cancel out, so C would be a plus 4. Okay? Hydrogen, when it's in a covalent compound, will be plus 1. So anytime I have a covalent compound, plus 1, plus 1, whoops, plus 1. H2O, O is a negative 2, 2 negatives, 2 positives cancel out. Since H is a plus 1, Cl has to be a minus 1. Since H is a plus 1 and I have 3 of them, N has to be a minus 3. So when I'm doing oxidation charges or oxidation states, they still have to cancel out. Okay? So we already did CO2 up above. We said oxygen is a negative 2. Because I have 2 of them, I'm going to have 4 negatives. My compound has to be neutral, so because I have 4 negatives, carbon has to be 4 positive. Okay? SF6. Fluorine is always negative 1. I have 6 of them, so I've got 6 negatives. My negatives and my positives have to cancel out. Because I have 6 negatives, I need to have 6 positives. Okay? NO3. The whole polyatomic ion has a negative 1 charge. My oxygen is a negative 2. I have 3 of them, so I've got 6 negatives. Well, because I have a polyatomic ion, it is not neutral, it has a charge. So I need something that when I add it to the negative 6, I'll still have 1 negative left over. So N has to be a plus 5. Plus 5 minus 6 equals negative 1. Okay? Now this is how oxidation states differ from charges. I can have non-integer oxidation states, so I can have fractions. Okay? In this case, oxygen is still a negative 2. I have 4 of them, so I have 8 negatives. Okay? Well, I've got 3 irons. I've got to get to a positive 8. I've got 3 irons to do it. That's not going to give me a whole number. It can't. I'm going to have a fraction for my oxidation number, and that's okay. Okay? Now what I'm doing is I'm figuring out oxidation numbers to keep track of who's gaining or losing electrons. So here's the way it works. CH4. We said H was always a plus 1 in covalent compounds. I've got 4 of them, so because I have 4 positives, carbon has to be 4 negative. Oxygen is an element in elemental form, so it has an oxidation number of 0. Over here, oxygen is in a compound. It's now got a negative 2. Because there are 2 of them, I've got 4 negatives, which means I need 4 positives to balance out. Hydrogen is always a plus 1 in a covalent compound. Oxygen is a minus 2. So I have all these oxidation numbers. Big whoop. This is why I need to keep track. Oxidation is loss of electrons. If I'm losing electrons, I'm becoming more positive. Reduction is gain of electrons. Since I'm gaining negatively charged electrons, I'm going to be more negative. Okay? So, an easy way to remember this, there are two different mnemonic devices. I like oil rig. Oxidation is loss of electrons. Reduction is gain. The other way we can do this is Leo, the lion goes grr. Loss of electrons is oxidation. Gain of electrons is reduction. I like this one better. It's just a little simpler, but a lot of people learn it. Leo, the lion goes grr. Either way works. So what I want to do is I want to look at my reaction, and I want to figure out who lost electrons or gained electrons by comparing oxidation numbers. Carbon started as a -4. Over here it's a +4. Because it became more positive, I know it lost electrons. It was oxidized. Well, I've got oxygen, which was 0. Now I've got oxygen, which is -2. 0 to -2, it became more negative. It was reduced. In an oxidation-reduction reaction, I always have to have both things happening. Somebody's gaining electrons, somebody's losing electrons. Okay? Now here's where it starts getting a little bit trickier. The oxidizing agent is going to be the electron acceptor, which means the oxidizing agent is the thing that is being reduced. The reducing agent is an electron donor, which means it's the thing that is being oxidized. Okay? So my reducing agent is causing somebody else to be reduced. My oxidizing agent is causing somebody else to be oxidized. So from the example above, since carbon was being oxidized, it is the reducing agent. Since oxygen was being reduced, it is the oxidizing agent. Whatever's being oxidized is the reducing agent. Whatever's being reduced is the oxidizing agent. Make sure to flip those.